I post the notes after class. I can't post them before I write them. Okay. So, we'll come back to that. All right. Next. So the next bit is measures of dispersion. Does anybody know what dispersion means? Sorry? Yes, exactly. How it's distributed, or literally it means the extent to which it's spread out. Okay. And this is because mean and median do not tell the whole story. So let's say we take a group of 5 men and get their heights. In my first group, I have guys who are 5'8", 5'10", 5'11", 6 foot, and 5'9". Now it's going to be hard to do calculations with that, so I'm just going to convert it to inches. In inches, that would be 68, 69, 70, 71, 72. Now I've got another group of 5 men. Their heights are 4'6", 7'4", 4'2", 6'8", 6'6". So in inches, that's 54, 88, 50, 80, and 78. So let's find the mean. So what is the mean for group 1? Can you tell, looking at group 1, can you tell what the mean is approximately? Yeah, not just around 70, it's exactly 70. Absolutely. Which is 5'10". Now what about group 2? Can you tell by looking at group 2 what the mean is going to be? It's exactly 70. If you add it up and divide by 5, you get 70 inches. So the average height in group 1 is the same as the average height in group 2. So those groups are almost the same, right? Right. What is the difference between the heights in group 1 and the heights in group 2? Right. In group 1, everyone is almost the same height. In group 2, the heights are spread out completely. Group 2 has greater dispersion. So we need, now obviously average does not measure that. So we need something that measures that. So what is a really, really simple way to say how spread out the data is in group 2? Can you think of a really simple way numerically, like with a number, to describe how spread out the data is in group 1 versus group 2? So Oshra, you said between 4, 6 and what? Oh, better than that. Between 4'6" and what? Yeah. Okay. Oh, 4'2". You're quite right. Yeah. So one way to say this. Right. So one way to describe this is to talk about from the lowest to the highest. So if you look at lowest to the highest, what do we have for group 1? Right. But now if we want to summarize that using one number, what would that one number be? If you want to express how spread out that data is using one number, instead of saying from 5'8" up to 6 feet, what could you say? Look at the inch numbers. That'll be easier. Instead of saying from 68 to 72, what could you say? 4 inches, and that's it. That's called the range.
Wait, what did you say? Wait.
Group 1, highest minus lowest. Right. The difference between the highest and the lowest.
Oh, the range.
Right, and we're going to call that the range. So the range is 4 inches for group 1. What about for group 2? You would get 88 minus 50. So group 2 has a range of 38 inches. Notice that it is now immediately obvious that these are that group 2 is much more spread out. Okay. So this is a very, very simple measure. Notice that this is greatly affected by an outlier. What happens if, what's the salary range in this class? I set the range, not the average, the range.
Including Bill Gates?
No. In this class right now.
What was the top one?
In this class, right, I said from 20 to 30. Right. 30 minus 0, so 30,000. If Bill Gates walks in, what's the range? Right, if Bill Gates walks in, the range is $1 billion. So range again is greatly affected by an outlier. Okay, so let's try to come up with. So what I'm going to now show you is another measure of dispersion, and we're going to be using it a lot for the rest of the semester. It's a little hard to explain. Notice that the range calculation is very obvious. It's intuitive. The next number that I'm about to show you where it comes from is not going to be intuitive at all. You're just going to have to use it a little bit and get used to it. Maya.
Okay, but isn't there a problem with the range also? Because if you say the range of the salaries of the tax including Bill Gates, maybe if you're 1 in a billion chance of getting one. Like, isn't there?
There's not a 1 in a billion chance. I'm just telling you what it is. It's $1 billion minus 0, so the range is $1 billion. It's just the range is what it is. The question is, how useful is it?
Yeah.
Okay, that's all. I agree, it's not as useful, so I'm going to show you a different measure. Yeah. Right. All right. So, here's the next thing. Standard deviation. So I'm going to show you how to calculate standard deviation for group 1. Okay. So, here's what we do. First, you have to calculate the mean. And remember, the mean for that group was 70. I take the first data value, which is 68, and I subtract 70. Then I square it. I do this for every data value. So I'm going to go back and fill in some details. So notice that the first one is negative 2 squared, that's 4. Next one is negative 1 squared, that's 1. That's 0 squared, that's 0. 1 squared is 1, and 2 squared is 4. So I take all those numbers and I add them up. And then I'm going to divide by 5, and 5 is the amount of numbers that I have. I'm going to divide by 5 minus 1. I'll explain the minus 1 at some point. And then we're going to take the square root of this whole thing. So this winds up being the square root of 10 divided by 4. Square root of 2.5, which is approximately 1.5811. So let me go back and fill in the details on the original step. 70 is the mean, like I've indicated there. Okay. So here's how you set this up. Again, each data value minus the mean, you square it. Then you add all those pieces up. Then you divide by, we have 5 data values, you divide by 5 minus 1. And then once you do that, you take the square root of the entire thing. So this is our first serious numerical calculation. Yeah.
Why is it minus 22?
I didn't yet. It's a little hard to explain. We need to know a little more first.
So whenever we do standard deviation, that's how we can do it.
Uh-huh. Okay. So why don't you guys go ahead and find the standard deviation for group 2. There's your data, and remember that we already calculated the mean, and it is 70. Sorry. Okay, so let's figure it out. So how does this go? What do we do? Any order you like. I'll keep it in the order it was written, that's fine. 54 minus 70 squared. Sorry? 80 minus 70. Okay. And what's missing? Square root. Okay. Next. Okay. So that's 256 and 324 and which is okay. Right. Okay. 16.91. Well, what we're going to see, again, this is the beginning of the serious calculations. We're going to be using standard deviation a lot this semester, basically now and until the last day. And what you're going to see in the future is that our calculations are very sensitive to standard deviation. So it's good to take it to 4 decimal places.
So we need to basically memorize that.
Memorize. Is it difficult to understand what to do? That's all you need to do?
That's the standard deviation.
Yeah, pretty much. Okay.
But the numbers will always come in that simple form.
I'll give you numbers, you have to do a calculation. That's about it. Okay. So this is the standard deviation. A couple of notes. First of all, in the course of this calculation, notice that in the second to last step we said the square root of 286, and that gave us 16.9115. 280, just the number 286, is called the variance. It's important for, I guess, more advanced statistics. We're not going to use it that much. We're mostly going to use the standard deviation, but you should know what the variance is. Okay. So notice that once you have the variance, how do you get the standard deviation? Square root. So once you have the standard deviation, how do you get the variance? Yeah. So for example, if the variance is 9, what's the standard deviation? Oh, I'm sorry, I flipped it right. If the variance is 4, excuse me. The variance is 4, what's the standard deviation? If the variance is 4, the standard deviation is 2. If the standard deviation is 9, what's the variance? What's it? 81. Right. I mean, again, we're going to be working with the standard deviation. You should simply be able to identify the variance. Yes. I mean, this is the standard abbreviation. You'll notice I tend to use a lot of abbreviations because I don't like writing everything out. Okay. And in fact, it's funny that you should mention that because right now we're about to learn the actual notation for these things. Not abbreviations, but the statistics notation for formulas and such. Okay. And here we go. Okay. So before we begin, we have talked previously about having a sample versus having a population. So the first thing you'll need to notice is that there's a different notation for everything depending upon whether you're talking about a mean or a sample or population. For example, what's the notation for mean? Well, if it's the mean from a sample, you write this, which is called x bar. However, if it's the mean for a population, you write mu. It's a Greek letter. I'm sorry? No. Just last time. It's a Greek letter. It's actually a mu. It's a Greek M. It's a lowercase m, but it really looks like a U. If you just kind of write like a U with a little tail on it, that's fine. Okay. But it's called mu. Think of it as mu. All right. So that's the notation for mean. Next, standard deviation. Again, it matters if you're talking about the standard deviation from a sample or standard deviation from a population. Standard deviation for a sample is nice and easy. That's S. The standard deviation for a population is sigma. Again, Greek letter. So you could think of it as an O with a little tail on it. You could write it like an O with a little tail on it. Next is variance. Variance is nice, it's nothing new. If you know the standard deviation, how do you get the variance? So variance is S squared, or sigma squared. Next, what about the size? So the size of a sample is called little n. The size of the population is called big N.
It's actually called little n. and big N.
Lowercase n, whatever.
Oh,
Yeah. No, regular letters. Regular English letters. Okay. Alright, now, so aside from the fact that we're talking about a sample versus a population, why do we have these two different sets of notation for these things? Well, there's a really, really important philosophical distinction between getting a value from a sample as opposed to getting a value from a population. If I ask, what is the average age of BMCC students? If I go out and ask every single BMCC student, I've got the average, and that's it. If I go out and ask every single BMCC student, then that would be the population, right? But what if I take a sample? Out of 20,000 students, I ask, say, 100. Is my answer going to be the same every time? Absolutely not. It depends on which sample I take. So all of these facts about all of these values for the population, think of those as fixed. Those are facts. However, when you calculate these values for your sample, notice that it kind of depends on your sample. Hopefully you have a good sample, right? But it does depend upon your sample. So the name for each of these things is when you get one of these values from the population, it's called a parameter. A parameter is fixed; it is what it is. However, when you calculate these values for a sample, it's called a statistic. A parameter is something you get from a population. Statistic is something you get from a sample. And again, the key distinction is that if you get it from population data, then it's a fact. If you get it from a sample, well, you know what? It depends upon your sample.
Okay, so I guess then the sentence would be a parameter.
Yes. Absolutely. Okay. And then there's one more piece of there's one more notation that we need. We have all these data values. We're always calculating using data values. So what notation do we use to represent data values? We just call that x. All right. So how do you calculate these things? Well, how do you calculate the mean for a sample? You just add up all your data and divide by however many you have. How do you calculate the mean for a population? It's exactly the same thing. So notice that the way to calculate a mean for a sample population is exactly the same. You just have to understand that you have to interpret it differently. If it's the mean for a population, it's a fact. If it's the mean for a sample, it's the mean for a sample, and hopefully it tells you something interesting. Okay.
Wait, but isn't the population usually bigger than the sample?
Yeah, absolutely.
So how can the average, how can the mean be the same?
The way you find it is the same.
Well, it could be. I mean, first of all, okay. So a little bit of philosophy, or I guess ahead of time. If you say you have a population and you take a sample, hopefully your sample is reflective of the population. So hopefully the mean from your sample is similar to the mean from the population. It doesn't have to be, but we sure would like it to be. Does that make sense? Okay. Okay. So very quickly, suppose we take 7, 10, and 16 that has a mean of 11. Find the standard deviation. Just tell me really quickly, how would we set this up?
7 minus 11 is
squared.
And minus 11 squared, divided by 3 minus 1, which is 2, and you add those up,
And you take the square root of the whole thing, right? So the first one is negative 4 squared is 16, negative 1 squared is 1, 5 squared is 25. Add it all up, you get 42 divided by 2, so square root of 21, which gives you 4.58. So now let's write down our answer to this question using our new notation. So how can we write down our answer using notation? We want to say the standard deviation is, but how do we write that?
Which part?
Okay. There you go. I made it a sample. So therefore you would write what? S equals 4.58. And since 21 is the variance, how would you write that part down? S squared equals 21. There you go. You guys are now well on your way to being professional statisticians. Okay. Now, any questions on this? Okay. Does anyone other than Maya have questions? Okay. Magdalena, do you have any questions? Okay. Well, the long way to do it is to say the standard deviation is 4.58, so let's square that, and you would get 21. The really quick way is to look at our calculation. The thing that you take the square root of is the variance. So so you can just pull that right out and say there's my variance. Okay. Now, back to this little devil called minus 1. Alright. So, first of all, what I'm going to do right now is I'm going to write down the formula in statistics notation for how you find the standard deviation. The only reason that I'm doing this is so that you see it and you're not afraid of it when you see it again. I don't care if you know this formula, I only care that you know how to calculate it. That being said, here's the formula. Okay, so what does this mean? S equals the square root of blah blah blah. Let's break this down. What is, where's my, okay. What is, well, first of all, what is this? Yeah, that's a data value. What is this? That's the mean. So that just means data value minus the mean.
Is that a line over the top of the X?
Yeah, it's the x bar, because what's x bar? X bar is the mean.
Yeah, oh yeah, okay.
Okay. And then we square it, and what is n? N is the size. So all we're doing is taking data value minus the mean, squaring it. Now, once we have data value minus the mean and square it, what do we do with that? Not quite. What do we have to do with them? We have to add them all up. And that's what this is well, it's a capital sigma, and that just means sum, or add them up. So that's all this formula means. So the formula means what you just did. Long story short. Okay. Now notice that this formula has been presented using the notation for samples. So we now have to re-express, if we want to say, well, what's the formula for population, we have to re-express this. But there's a hitch. When you calculate this formula for population, do not minus the 1. Because. Yeah.
So that's the same exact thing at the top.
Yes.
As the other
That
population,
formula.
and that's just the formula for it.
Yes, but notice that there's a distinction. For population, you're just dividing by the size, which is n. When you're doing a sample in calculating standard deviation, you divide by n minus 1.
It's the second letter in population median. That difference.
Yeah, you know what? That's a little sloppy. Sorry. Yeah, that's a mu. It kind of looks like an m. You know what? Some people write m, and I know what you mean. Okay.